Kirchhoff's law. Before to start Kirchhoff's law, we have to revise, or we have to know the difference between series circuit and the parallel circuit. What is the difference between both? Series circuit is one in which components are connected one after another, forming one complete loop and has the same current. Like what? I give you an example. For example, like this. This is a bulb, and then this is a resistor, okay, and then this is a bulb also, and so on. Then they are connected in series. In that connection, we have one path of the current. So the current is denoted by I. Of course, we mean conventional current. It is the same current. You can see it is the same current but through all components. So this is one loop, contains one current. So this is called the series circuit. Now, parallel circuit, no, is one where the current can take alternative routes in different loops. In parallel circuits, the current divides at a junction. So you can see here, this is a parallel, this is one parallel circuit. Here, this is the current, for example, this is I, this is the current, and then this is called junction. Can you see? This point is called the junction. The current I will split into, this is the current I at this junction, will be split into I1 and then I2. Then the current I split into two currents. So I split into I1 and I2. So this is the difference between series and the parallel. So remember, in series circuit, the current is the same. So remember, in series, current is the same. So the same current. But in parallel circuit, the voltage is the same. The voltage, okay? So the voltage is the same. So this is the difference between series and the parallel. مرة in series, the current is the same. So it is just one loop, one current. But in parallel, we have different loops. We have junction. And at this junction, the current I from the battery is split into I1 and I2 or I3 and so on. Now, we start Kirchhoff's first law. The rule is important, or the law is important here. This is Kirchhoff's first law. The sum of currents entering a junction, اللي داخل في الجنكشن, in a circuit is always equal to the sum of currents leaving it, current اللي خارج. Look, this is a junction. This point is a junction. Now, here we have I1. So this is the current in. From the arrow, we can decide, is it in or out? And then this is also I2, current in. This is I out. I out or I total equals I1 plus I2. Another example. You can see this is a junction. This point is called the junction. It is the point of connection of wires. So the current in is I1. The current in also is I2. So the currents in are I1 and I2. Then we can say I1 plus I2. I3 is out from the arrow. I4 also is out. Then I1 plus I2 equals I3 plus I4. So this is called the Kirchhoff first law. The sum of currents in equals the sum of currents out at any junction. Here, this is the flow in and this is the flow out. This is the mathematical formula of Kirchhoff's first law. Sum of current in, sum denoted by this summation, sum of current in equals the sum of current out. Sum of currents in equals the sum of currents out. Current, it means charge at the same moment. So we can say the sum of a charge in, the sum of a charge in equals the sum of charges out. Then the charge is conserved. So in Kirchhoff's first law, the charge is conserved. So this is important. So the charge is conserved in Kirchhoff's first law. Now, let us solve this example. Look at the example in front of you. I equals 8 ampere. So the current in is 8 ampere. Now we have I1, I2, I3 that are the currents out. I1, 2 ampere. So this is 2 ampere. I3 is 3 ampere. This equals 3 ampere. Find the value of I2. Then at this junction, so we write from Kirchhoff's first law, sum of currents in equals the sum of currents out. So 8 is the current in. Out we have I1 plus I2 plus I3. I1 is 2 ampere plus I2 is unknown. We need the value of I2 plus I3 is given 3 ampere. So then we can get I2. So 8, 2 plus 3 is 5, 5 plus I2. Then from this formula, we can get I2. So I2 equals 8 minus 5 equals 3 amperes. Do you understand?
Yes, Mr.
Very good. Now, try to solve this example. Check your answer with me. Now, in part A, this is part A, the current in is I, the current out is 2 ampere and 1 ampere. So at this junction, the current in is I, the current out is 2 plus 1. This is Kirchhoff's first law. At any junction, the sum of currents in equals the sum of currents out. 2 plus 1 is 3. Then I equals 3 ampere. Now, let us do part B. The current in is 0.5 ampere. The current in is 0.7 ampere. So the sum of currents in 0.5 plus 0.7. That is the sum of currents in 0.5 plus 0.7. The current out is only I. 0.5 plus 0.7 is 1.2. 1.2I, then I equals 1.2 ampere. Now, last part. I is current in. 2 also is current in. Then the sum of currents in equals the sum of currents out. The sum of currents in is I plus 2 ampere. Currents out is 4 ampere and 0.5. Then the sum of currents out is 4 plus 0.5. I plus 2 equals 4 plus 0.5 is 4.5. Shift 2 to the other side. then I equals 4.5 minus 2, which is 2.5 ampere. Okay?
Okay, Mr.
Yes. Okay. Now, next. Now let us resolve this example. The lamps in the figure are identical. Identical, it means that they have the same resistance, the same voltage, the same current. There is a current of 0.5 ampere through the battery. Then this is the positive pole of the battery and this is the negative pole of the battery. Then the current is 0.5 ampere. This is the current from the battery. What is the current in each lamp? Now this is a junction. You can see this is junction. So at this junction, the current will be split into what? Because the lamps are identical, then in each branch, the current will be the same. We have two branches. Then this is I1 in the first branch, and this is I2. So this is I1, it is the same here. This is until this is I1. And on the other branch, this is I2. This is I2. Now, I1 at junction, we say this is Kirchhoff's first law. Sum of current in equals sum of current out. Current in is 0.5, out is I1 plus I2. But because the lamps are identical, so we can say I1 equals I2 equals, for example, I. Then I1 plus I2, it's 2I. Then 0.5 equals 2I. Then I equals 0.5 divided by 2. So it is 0.25. So 0.25. Then I1 equals I2 equal 0.25 ampere. Then the current in each lamp is 0.25 ampere. So what is the current in each lamp? So the current in each lamp is 0.25 ampere. Okay, do you understand this question?
Yes, Mr.
Very good. Now, next part. Try to solve this question. It comes in final exam. Try to solve it.
Inshallah.
Determine the current flowing between A and B. So we need the current between A and B. Let this current denoted by I. Now we need the current I. But we don't know the direction. Okay? So he said between. But now we can decide the direction at junction A. Look, please, at junction A. Now I ask you to decide, is that correct or no? The direction of the current. Think of this one. What is the direction of the current between A and B? Is it in or out? Between A and B. You can see here at junction A, the current in 0.5. The current out 0.3. So because the current in greater than the current out, then at the AB, between A and B, must be the current out. Then it must be like this. Why? Because 0.5 greater than 0.3. The current must be positive. Then the current in direction from A to B. How can we decide? Just to compare between the current in and the current out. Now, at junction A, the current in is 0.5 equal, the current out is 0.3 plus I, this is also current out. Now, shift 0.3 to the other side. I equal 0.5 minus 0.3 equal 0.2 ampere. Then the current between A and B is 0.2 ampere, and it's from A to B. The second part, he said calculate Ix. Now, at junction B, now complete the solution to find Ix. At junction B, the current in is I. So this is the current in from the arrow we decided before. 0.1 ampere, it's out. Ix also is out. Then the sum of currents in, it is just I. The sum of currents out, 0.1 plus Ix. I already, from the first step, we found it 0.2. Then 0.2 equal 0.1 plus Ix. Shift 0.1 to the other side, then Ix equals 0.2 minus 0.1 equal 0.1 ampere. Okay, so all of these part about Kirchhoff's first law. Now, next we talk about Kirchhoff's second law. Kirchhoff's first law talk about junction, but Kirchhoff's second law talk about loop. Now, the sum of EMF around any loop in a circuit is equal to the sum of potential difference around the loop. What do you mean by loop? Closed loop, like this. This is a bulb, this is a resistor, and this is a bulb, and this is a bulb, and this is a resistor. And then here we have one cell. Then this is called the closed loop. This is one loop. This is a loop. He said, the sum of EMF is the potential difference of the sources. For example, here we have EMF, one source, equal the sum of potential difference. Around this one, this is potential difference. We can say it's V1. This is another potential difference, V2. This is V3. This is V4. Then the sum of EMF is E1 equals the sum of potential differences, V1 plus V2 plus V3 plus V4. Mathematically, we use this formula, the sum of EMF equals the sum of potential difference. Here we talk about energy. Energy gain equals energy loss. Energy gain inside the battery, energy loss outside in the bulb, in the resistor, and so on. We can do this mathematically like E1 plus E2 minus IR1 minus IR2 equals 0. Here the energy is conserved because the sum of the energy in equal the energy out. Energy in, gain in energy in the batteries or EMF equal lose in energy in the potential. So the energy is conserved. Okay, so here energy gained passing through the source equals energy lost passing through the component. Then the energy gain per coulomb around the loop equals the energy lost per coulomb around the loop. Then the energy is conserved. So in any circuit, energy is conserved. So remember, in Kirchhoff's first law, we have the point or the word junction. In Kirchhoff's second law, we have the word loop. Kirchhoff's first law, charge is conserved. Kirchhoff's second law, energy is conserved. So this is the comparison between Kirchhoff's first law. So this is Kirchhoff's first, and this is Kirchhoff's second. Here in Kirchhoff's first law, we have the word junction. In Kirchhoff's second law, we have the word loop. In Kirchhoff's first law, charge is conserved. In Kirchhoff's second law, energy is conserved. This comes in the multiple choice. Energy is conserved in what? In Kirchhoff's second law. Charge is conserved in what? Kirchhoff's first law. Now, sometimes we say this is loop law. Sometimes we say this is junction law. Now, this is very important part. How can we solve any question by using Kirchhoff's second law? Now, here it depends on the direction of the current in the loop. So if the current in the loop from A to B, then the potential difference is negative. And also, if the current from B to A, the potential difference is negative. Here we say this is the negative and this is the positive. Then we have here the direction of electron flow. The electron flows from negative to positive. Now, if the direction of electron flow is the same direction as the current, so it's positive. Then if the current from B to A, the same direction as electron flow, then EMF is positive. But if the direction of the current in the loop is opposite to the direction of electron flow, EMF is negative. Let us resolve the questions about this. Now, look at this question. Find the current in opposite circuit. Look, please, guys. First, we have to put the direction of electron flow. It's fixed. This is the direction of electron flow. It is separate to the direction of the current in the loop. Now, we suppose that the current in the loop denoted by I. Let the current is I in this direction. Any direction, no problem. Now, here we have a cell, 3 volt, and we have another cell, 12 volt. Then we have to put the direction of electron flow in the other cell. Now, we started to solve. How can we start to solve the question? We start at any point. For example, we start in this point, and then we go around the loop in the same direction that we suppose, the current I. Now, we start from the point B. From the point B to C, here we have resistor. So the potential difference is negative. So it's a negative 5I. The current is I. Now, we go in this direction. The loop direction or the current in the loop is opposite to the direction of electron flow. Then it's negative. So we write minus 12. And then we go in this direction. The current is I. So in case of resistor, it is different. It is negative potential difference. So it is negative 6I. Now we go in this direction. The loop direction is the same as the direction of electron flow. So it's a positive 3. We reach to the point B. We start at B and end at B. Then the answer is 0. So this is the way to solve any question by using Kirchhoff's second law. Now we collected the like terms. Negative 5I and negative 6I, negative 11I. Negative 12 plus 3, negative 9. Negative 9 equal to 0. Shift negative 9 to the other side. So negative 11I equals 9 divided by negative 11. So I equals negative 9 over 11 ampere. This is not question like the questions of the exam. It is just example. Now the current is negative, then we suppose the current I clockwise. Then the current is I is anti-clockwise. So we write the current in the circuit is positive 9 over 11 ampere, but in opposite direction. It means anti-clockwise. Okay, now let us see another example. Now try to solve this example. Okay, try and then I help you, but try first.
Inshallah.
Calculate the charging current. We need I. Of course, here the direction of the current from the higher voltage to the lower voltage. And already we have the direction of the current. This is the direction of the current. From higher, this is 14 and this is 12. Then this is higher voltage and this is lower voltage. Then the current from higher to lower. Start. Already we have the direction of the current. Then at this point, but before to start, we have to put the direction of electron flow. It's from negative to positive. So this is the direction of electron flow. Now we go in this direction because this is the direction of the loop. Here we can start from this point. Then here the direction of the current, the loop direction, is opposite to the electron flow for 12 volts. So it's negative 12. Why it's negative? Because the direction of current is opposite to direction of the loop. So this is the direction of the current, but this is the direction of electron flow. It's from negative to positive. It's opposite to the direction of the current in the loop. Then it's negative 12. Now, this is a resistor, so the potential difference is negative. So it's a negative 0.04 I. Also here we have a resistor, so the voltage is negative, the potential difference is negative, so it is negative 0.5 I. But in the 14 volt, the electron flow, it is the same direction as the loop direction, then it's positive 14. So plus 14 equals 0. Now we use the calculator to collect the like terms. Here, negative 12 plus 14, it's positive 2. And now the negatives for the I, here, negative 0.04 plus negative 0.5. So we write 0.04 plus 0.5 because both of them are negative. Then the answer is negative 0.54 I. Equal what? Equal 0. Shift the negative to the other side, then 2 equals 0.54 I divided by 0.54, then the current is 2 divided by 0.54. 2 divided by the answer. So the answer is 3.7. So the current in the circuit is 3.7 ampere. Now let us solve the question that came in the final exam. This is the this ideal question that the same as questions of the past paper. Okay, now look at this question. This is from past paper. I said consider the circuit below and calculate the value of I2 and I3. Now, we start with junction here. This is junction. We can say this is junction A. Or we can choose this point. It is junction. No other junction. The junction is the point at which all the currents meet together. So at junction A, now we use Kirchhoff's first law, and then we use Kirchhoff's second law. At junction A, the sum of currents in. Now let us see the current in the circuit. This is I1. Then I1 start from this I1. Here, this is I1. And then end at this. So this is I1. So the current in is I1, which is 16. But we write I1 first. I1. Now, I3 start from A and end at this junction. This is I3. It's out. So In is I1 and I3 is out, I3. Also, I2, you can see here, I2 is out. I2 is out at junction A. Then I1 equals I3 plus I2. I1 already is given 16 ampere. So we write 16 equals I3 plus I2. Let this equation is equation number 1. So this is I2 Let this equation number 1. Now, we use loop. We can use the first loop, so we can use this loop. How can I choose the loop? It depends on the cell in the loop. We have just one cell, 80 volt, then this is the positive and this is the negative, then this is the direction of the current. So we take loop 1. Then loop 1, it means we use Kirchhoff's second law. Loop 1. Now start at this point, but we have to put the direction of electron flow. Electron flow, this is the direction of electron flow. This is the direction of electron flow. And then we go through the loop 1. Now, first here, loop 1, the current in the loop, it is the same direction of electron flow. So the EMF is positive. So it's 80 volt, positive. Now, here, in this branch, the current is I3 and the resistor is 4. So it's negative 4 I3. And then we go on this here. So this is I1 here. I1 and the resistor is 2. So it's negative 2 I1. We reach the point, then the answer is 0. I1 is given, which is 16 ampere, then 80 minus 4 I3 minus 2 multiply I1 16 equals 0. 2 times 16, it's 32. 2 multiply 16, it's 32. Then we write 80 minus 32, 2 times 16, minus 4 I3 equals 0. 80 minus 32, it's 48. Then 48 minus 4 I3 equal to 0. From this, we can get I3. Shift negative 4 I3 to the other side. Then 48 equals 4 I3. Divide by 4, then we can get I3. 48 divided by 4 equals 12 ampere. Then this is the value of I3. Substitute in equation 1. So 16, so we write from equation 1, 16 equals I3, 12 plus I2. Now we can get the value of I2. Now just shift 12 to the other side. So I2 equals 16 minus 12, then I2 equals 4 ampere. Okay, now we calculated I2 and I3. Okay, next example. Let us see this example. Try to solve part I. Try to solve alone part I, and then I help you. But try first. Okay, let us we think together about this. Of course, we start with Kirchhoff first. He said calculate I1 and I2. Now, at junction A. So this is the way of solution. So we start at junction A. Now we look at the current. The current in is 2 ampere. The current out is I1. The current out is I2. Then at junction A, current in is 2 and current out is I1 plus I2. Now we can leave this equation number 1 because we have 2 unknowns. Then we need another equation. Already we said loop 1 and loop 2. So we use loop 1. Now we go to loop 1. We apply Kirchhoff's second law. Before to start loop 1, we have to put the direction of electron flow. So this is the direction of electron flow. Also here, this is the direction of electron flow. But just we look at the loop 1. Now we can start from any point. This is the loop. We can start from this point and go around the circuit in the same direction of the loop. Now we go in this direction. This is 2 ampere, nothing in that branch. Here I1, so the current is I1 and the resistor is 4. So it's a negative 4 I1. So negative 4 I1. And then we go in this direction. Then the direction of the loop, it is the same direction of electron flow. So 6 volt is positive. So plus 6 equal 0. Equal what? Equal 0. Now we can get I1. How? Shift 6 to the other side. Negative 4 I1 equals negative 6. Divided by negative 4, then I1 negative 6 divided by negative 4, it is 1.5. We check 6 divided by 4 equals 1.5 positive, because negative cancel with negative. So it's 1.5 ampere. Now substitute in equation 1. So we say from equation 1, 2 equals I1 is 1.5 plus I2 unknown. Shift 1.5 to the other side. Then I2 equals 2 minus 1.5 equal 0.5 ampere. Now we got I1 and I2. This is the first part, I. Now the second part, he said find the resistance R. Now we need to solve the second part. To solve the second part, we go to loop 2. Loop 2. Follow me. Now we need to write the equation of Kirchhoff. Okay, this is the direction of the loop. We start from this. We can start at this point. Now we go in this direction. I1 is the current and the resistor is 4. So it's negative 4 I1. Now we go in this direction. This is the current. What is the direction of the current in this? This is I2. You can see this is I2. Now here, take care. The current I2 is opposite to the loop. Then here we have double negative because the current is opposite. Then we write negative, negative. R I2. Okay, and then this is the electron flow. It is the same direction of the loop. So it's positive plus 3 equal what? Equal 0. Now we can solve this equation. Already I1 is 1.5. So negative 4 times 1.5, negative times negative positive. I2 is 0.5, so it is 0.5 R plus 3 equals 0. Now we use the calculator. Negative 4 multiply 1.5 plus 3, it's negative 3. Then we write negative 3 plus 0.5 R equals 0. Shift negative 3 to the other side. So 0.5 R equals 3. Then we can get R equals 3 divided by 0.5. So 3 divided by 0.5 equals 6. 6 what? 6 ohm. R equals 6 ohms. We can solve this part in another way, but I prefer this way to understand how can we put double negative. It's okay? Because sometimes we have many components in the same branch. So I need from you to understand this way. When we put double negative, if the current is in opposite direction of the loop. Now, next part, we talk about resistors in series and parallel. Now, this is the resistors in parallel. We have different currents. So this depends on Kirchhoff's first law. We don't need to prove. I proved here. You can do it. So here in resistors in parallel, R total, just we need to understand this, R total equals 1 over R1 plus 1 over R2 plus 1 over R3, all to the power negative 1. This is resistors in parallel, 1 over R. Of course, the total resistance will be less than the minimum value of any resistance. Okay, now this is R total. Now, in case of resistors in series, R total is the sum. So R total equals R1 plus R2 plus R3. In case of resistors in series, R total is greater than the greatest resistance. In resistors in parallel, R total is less than the smallest resistance. But in resistors in series, R total is greater than the greatest resistance. Let us resolve the question about this. Yeah. Determine the equivalent resistance of the complex circuit shown in the following. We need R total. Now, how can we solve this question? This 2 and 6, they are series. How? Because they have the same current. Then we can add them. Then R total 6 plus 2 equals 8 ohms. And then 8 ohms and 4, they are parallel. Then we can get R total of this branch. So R total equals 1 over 8 plus 1 over 4 all to the power negative 1. We use the calculator. Fraction 1 over 8 plus fraction 1 over 4. Close the bracket, all power negative 1. The answer is 8 over 3. Okay, so it's 8 over 3 ohms. Now they are in series. Then we can get R total. Now R total for the whole. So R total equals 3, it is series, plus 6, it is series, and the total resistance of this combination is 8 over 3. So 8 over 3 plus finally 1 ohm. Now we use the calculator to get the answer. So this is plus 1, plus 6, plus 3. So the total is 38 over 3 or 12.66, approximately 12.7 ohms. So this is the equivalent resistance. Okay. Here we have parallel. This branch is parallel. So R total for this branch is 1 over 7 plus 1 over 10 all to the power negative 1 because they are parallel. Now bracket fraction 1 over 7 plus fraction 1 over 10, close the bracket to the power negative 1. The answer is 70 over 17. So this branch equals 70 over 17 ohm. Now we can calculate the equivalent resistance. Equivalent resistance, it means R total or R equivalent. So we have here 4 plus 70 over 17 plus 9. Now this value plus 4 plus 9. So the answer is 291 over 17 or 17.11. So 17.11 ohms. 17.12, sorry. Okay, ohms. Now calculate the current in each resistor. If the potential difference here, the potential difference equals. Now in part B, we can get R total. This is R, sorry, I total. This is I, and here this is I. Now we can calculate I through 4 and 9. How? We use Sambusa law. V equals IR, then I total. So I equals V total over R total. V total is 34 divided by R total, which is 17.12. So we write 34 divided by the answer. So it's 1.98. So it's equals 1.986, 1.99 ampere. Then the current. So the current in 4 ohms equal the current in 9 ohms equals 1.99 ampere. What about the current in 7 and 10? Now here we calculate the voltage around 4. We say this is V1, and the voltage around 9, that this is V3, and then we can calculate V2. Now, okay, V1 equals I multiply R1. I, the current from the circuit, which is 1.99. So 1.99 multiply R1 multiply 4. 1.99 multiply by 4. So the voltage is 7.96 volt. This is V1. So the voltage in this 4 ohm is 7.96 volt. What about V3 through 9? So V3 equals I R3. I is the current from the circuit multiply R3, which is 9. So 1.99 multiplied by 9 equals 17.91 volt. Now we can calculate V2. The total voltage is 34, so we can calculate V2 in the parallel branch. So V2 equals 34 minus open bracket, V1 is 7.96 plus V3 17.91. We can get this value. So we write 34 minus open bracket 7.96. Sorry. Again, 34 minus open bracket 7.96 plus 17.91, close the bracket, equal. Then the voltage is 8.13 volt. The two resistors 10 and 7 are in parallel. They have the same voltage. Then we can get I1 here. This is I1, and then this is I2. I1, it is the current in 7 ohm. Then I1 in 7 ohm equals V over R. V is the same voltage, V2, here, it's 8.13, divided by R. R is 7. So divided by 7. So 8 divided by 7. Then the current is 1.16 ampere. What about I2? I2 is V over R. V, it is the voltage, the same voltage because they are parallel, 8.13 divided by R. R is 10. So 8 divided by 10, it is 0.81 ampere. Okay.